Welcome to Chapter 5. In this chapter, we are going to introduce molecules and compounds. Now, we've kinda, sorta already talked about these, just kind of in passing at a few different points in the previous chapters, but now we're going to really jump into this topic of taking atoms and combining them together. Because truthfully, the universe would be a really, really boring and dead place if the only thing that could exist were singular atoms. If atoms could not come together to form more complex structures, like molecules and compounds, the universe would, it wouldn't be anything like it is today. There would be no life, for example, in the universe. Now, when things do come together, when different atoms come together to make a molecule, the properties of that new thing that is made can, and usually are, very different. They can be, and they usually are, very different from the elements that made the molecule. So for example here, over here we have a little droplet of sodium. That's what was at the bottom of the beaker here in this GIF. And that's a little droplet of water falling onto the little piece of sodium. And when they come into contact with each other, it explodes. This is because sodium metal is highly, highly reactive, especially with water. It is, as you can see, literally explosively reactive with water. We don't normally think of water being super reactive, but it is definitely very reactive with sodium metal. Another thing that's also very reactive is chlorine gas. Now, chlorine gas is so reactive that it's actually used as a chemical warfare agent. It is deadly if you breathe in chlorine gas. But if you take sodium metal, super reactive metal that explodes when it comes in contact with water, and super deadly chlorine gas, put them together, and you get table salt. Sodium chloride, which we put on our food all the time. So take two super reactive deadly things, put them together, and you get a nice savory salt that we put on our food. Well, nice in moderate amounts. Don't use too much. Similarly, if you take hydrogen gas, which is highly explosive, very, very flammable hydrogen gas, which if you've ever heard about the Hindenburg, you know that. That's the Hindenburg there, burning. They used hydrogen gas in that Zeppelin. And you combine hydrogen gas, which is super flammable, with oxygen, which is actually required for combustion to happen to anything. If something is going to burn, it has to have oxygen to react with it. So oxygen, required for things to burn. Hydrogen gas, super flammable gas. Combine them together, and you get water, which we use to put out fires. So, the compounds that we make from elements can have, and often do have, dramatically different properties from the elements that they are composed of. Just because you take something that's very dangerous in its atomic form and you make it into a compound does not necessarily mean that the thing that you're making is going to be dangerous. Sometimes it is, but often it is not. So, a few things about compounds here. When you're investigating a compound, you will always know exactly what the proportions of the constituent elements are. That is what we call the law of constant composition, I believe is what that's called. Essentially what this says is, if you have a sample of water, you will always have one oxygen for every two hydrogens. Water has the formula H2O. If you have something other than H2O, you do not have water. If you have, for example, H2O2, it's just a little bit different than water. in terms of its formula, but that is a dramatically different molecule. H2O, we drink to stay alive. H2O2, which is hydrogen peroxide, if you drink that, you will not be alive for long. It will kill you. So, molecules have constant composition. Every molecule of a certain compound will have the exact same composition. A scientist by the name of Joseph Proust was the first person to really state this idea formally. And so we actually kind of already talked about a little bit of this here, but as the example that I give here again is water. So you have 2 atoms of hydrogen for every 1 atom of oxygen. And then conversely, the masses are also going to be going to have a constant composition, essentially. So you're going to have 16 grams of oxygen for every 2 grams of hydrogen. Since the particles themselves are proportional to one another, they always stay in that 2 to 1 proportion. The masses are also going to be proportional. Now, they're not going to be the same proportion. So you notice here, this is not 2 to 1, this is 8 to 1. And that's just because the particles have different sizes. If the particles were the exact same size, then they would maintain the same mass-to-mass proportion. When we are writing molecules, we write what we call chemical formulas, which we've already seen quite a few of up to this point, but just to spend a little bit more time and go into a little bit more detail on these, we have kind of 2 different options when we're writing out these chemical formulas for the numbers, and then really only one option for the letters. The letters are always just going to represent the symbols for the elements. We're never going to have any other letters. If you have a letter in the chemical formula, it is representing an element. When it comes to numbers, things can be a little bit different, though. If we're looking at just a single molecule, then we should only have what we call subscripts. So the subscripts are the little numbers down and to the right of the letters. These indicate how many of the atom that it's attached to that you have in the molecule. So H2, the 2 here is telling you you have 2 hydrogens. If there's no subscript at all, like this one, then it's implied that you have a 1 there. We just don't write 1s in because it's impossible to have a 0. Because there's, if you have 0 of an element in a molecule, then why would you write the formula in the first place? Why would you write that element down if you didn't have any of it? So if you just write the single symbol, then it is implied that you have 1 of that thing. The other way that you can write numbers in, which we'll talk about a little bit later, is if you put a number at the beginning. So if, for example, we had a 2 here, the 2 at the beginning tells us that we have 2 of everything that follows. So this is what we call a coefficient. And like I said, we'll talk more about coefficients later. For now, we're going to focus on the subscripts, so the little numbers here, which tell you how many of each of the elements you have in your compound. When we're writing out the names, so when we're writing out the formula, there is actually a general rule for which element comes first. The way this normally works is if an element is farther to the left on the periodic table, then that element is going to be farther to the left in the formula. So they follow the same rule, essentially. Things that are farther to the left on the table go farther to the left in the formula. Now, if you have things that are in the same column, so for example, oxygen and sulfur are in the same column on the periodic table, and you can have molecules that have, for example, 2 sulfurs and an oxygen, or 1 oxygen and 2 oxygens and a sulfur. Like there's multiple ways you can combine oxygen and sulfur. If they're in the same column, the element that is lower on the table is the one that we put first. in the formula. So if, for example, we had a molecule with a single sulfur and 3 oxygens, that would be SO3. They're in the same column, so the one that's lower down, which is sulfur, goes first, and then we have 3 oxygens, and so we have O3. And the fact that there's no number with the sulfur just tells us that we have only one of that sulfur. All right. One slightly more complicated way of writing some of these formulas is if we have what we call polyatomic ions, which we'll talk more about later. These are groups of atoms that stick together, essentially. So the example that's given here is magnesium nitrate. This NO3 minus is what we call a nitrate group. And this molecule has 2 of them. And so instead of writing out MgN2O6, which would technically still be correct, but it doesn't give you as much information as MgNO3 2. Because when it's written out this way, you're being told you have 2 NO3s. Whereas if it's written out like this, you don't really know how the nitrogens and oxygens are connected together. So when you have a situation like this where you have something in parentheses, that's the person that wrote that telling you these are one unit. They're going to stick together. And then the number outside of the parentheses tells you, and you have, for example, in this case there's 2, so you have 2 of everything in the parentheses. So if we look at this example here, we would have 1 magnesium, 2 nitrogens, and 6 oxygens in that molecule, which would give us 9 atoms total, I guess. And so this is one way of representing what that molecule would look like. If you were to actually shrink down to the size of atoms, it wouldn't quite look like that, but it's a decent representation. Similarly here with aluminum sulfate, that's what this would be called. Here we have 2 aluminums, and then we have the sulfate in parentheses and a 3 outside the parentheses, which tells us that we have 3 sulfate groups. And so if we were to count up the atoms here, we would have 2 aluminums, we would have 3 sulfurs, and we would have 12 oxygens, which is what you can see down here. And again, these two are not the same, because this is giving you extra information. It's not to say that this isn't, I'm not saying this is wrong necessarily, but it is definitely not as useful as this, where you're given extra information saying that you have sulfate groups. Whereas over here, you don't know. You don't know what's going on. You just know that you have these atoms present. All right. I think we'll go ahead and call it there for this video. In the next one, we'll talk about a few different ways of representing molecules, and which one of these different ways of representing it, our reasoning for picking one or the other is mostly just how much information do we want to convey. So we'll take a look at that next time.